Hello again, and welcome back to part 4 of the Plant Light project. Today we're going to talk about the LED driver circuit that will regulate the current passing through the LEDs in the plant light. This design will use a switch mode power supply controller designed for current regulation through LEDs. Before we dive into how this current regulating switch mode power supply controller works, let's talk about the requirements and limitations that are driving my design decisions. Let's start with the requirements. There will be one LED controller per color. This will limit the scope and complexity of the design to 5 LED controllers. Arbitrary brightness adjustment to tune each LED channel is also required. This will allow for the fine-tuning for the spectrum of the light emitted from the lamp and will allow us to set the light intensity to prevent overexposure in particularly sensitive plants. The limitations of this design come from the way that LEDs fundamentally operate. LEDs don't allow for current flow until their forward voltage is exceeded. For more information about this and how LEDs work, check out my video that talks about that. Therefore, we must select an appropriate number of LEDs that will accommodate our 24-volt input voltage, since we've selected a step-down constant current controller. This requires that the forward voltage of the LEDs, times the number of LEDs required to achieve the brightness we desire, must be set to less than 24 volts, leaving some margin for the voltage drop across the current regulation circuitry. It would be ideal to have the different LED colors distributed evenly throughout each other to achieve the best color mixing. We'll talk more about my layout and placement of the LEDs in part 5 of the Plant Light project. Now let's consider the forward voltage requirements of the LEDs we chose in part 1. We'll start with the red and blue LEDs. The red LEDs have a forward voltage of 2.2 volts at 350 milliamps, which will produce at least 39.8 lumens per LED. Our 24-volt input voltage divided by 2.2 volts will be equal to 10.9 LEDs. Since 10.9 LEDs is not practically achievable, our limit is 10 LEDs. For the blue LEDs, with a forward voltage of 3.3 volts at 350 milliamps, they will produce at least 23.5 lumens per LED. Given our 24-volt input voltage, this will result in a maximum of 7.2 LEDs, or 7 LEDs. Here are the rated forward voltages and light outputs for the green, warm white, and infrared LEDs. Now that I've mentioned the requirements and limitations imposed on this design, let's head over to the computer to examine the schematic that I ultimately created, and let's talk about how this switch mode power supply controller is regulating current through the LEDs. Let's go! Now that we're at the computer, let's talk about the schematic shown here. There are a few sections. First, the LEDs, which were selected in part 1 of this series. There are then the LED drivers, which we will discuss today. Next, there's the connector to the control board, which we'll cover in a coming video. The protection and filtering circuits, which were not originally in the design, are shown here, as well as at the voltage input. These were not originally in the design, but turned out to be essential. We'll talk more about this in a coming video. Finally, there are the 12-volt and 5-volt buck converters, which we've already discussed in parts 2 and 3 of this series. Let's start with these LEDs. When looking to arrange the LEDs, I finally decided on a 6x5 grid of LEDs, with approximately half-inch spacing between the centers of each LED. How I distributed the 30 LEDs amongst the different colors was 6 green, blue, and white LEDs, 8 red LEDs, since their brightness is typically a little bit less than green, blue, and white LEDs, 4 infrared LEDs, in part because they're very expensive, and in part because I don't need much infrared light for the plant light. These LEDs will result in a total intensity of at least 1,442 lumens, plus the infrared. Since lumens only measures visible light, infrared light cannot be added to this number directly. The light output intensity of 1,442 lumens was calculated using the minimum rating on the datasheet. I hope to measure the actual performance of the LEDs in a future video. You'll notice that each channel has a 0 ohm resistor across an LED. This is to make accurate current measurements by shorting out one LED. Now let's talk about the LED controllers. For this project, I designed one switch mode power supply current regulator for the LEDs, and then duplicated that schematic element 4 times, one for each color. This is a step-down switch mode power supply, and it does not use a traditional topology, placing the load in series with the inductor. To disable each LED channel by default, and to prevent the LEDs from flashing for a moment before the microcontroller powers on, a 20 kilo resistor biases the transistor, which disables each LED controller by default. You can see that circuit here. When the microcontroller drives the transistor base to less than 0.7 volts, approximately, this transistor will turn off and the LED channel will be allowed to turn on. This will be used for PWM controller to change the brightness of each LED channel from 0 to 100% of its maximum value. We'll talk about the Schottky diodes and input power filter in a future video and why this was required, since it wasn't in the original design. Moving on to my design of the LED driver, let's open one of these switch mode power supply controller. Now this is actually a clever use of a voltage regulator, tweaked slightly to achieve current regulation. This controller has an integrated low side switch and featured a reference design in the datasheet, which I leveraged when creating this schematic. I used the same rectifying diode as I used in the buck converters, since the diode I already selected met the current requirements of this circuit. In this case, current enters at the input pin, labeled V drive here. It then passes through the 0.3 ohm resistor, creating a voltage drop which can be monitored at the set pin. This current continues to flow through the LEDs, through the inductor, and then to ground, through the low side switch. When the low side switch is off, the current is then flowing through this diode back to the input voltage. In this case, the value of this resistor sets the maximum current output of the controller, since it's truly regulating the voltage drop between the V-in pin and the set pin. Changing this value will adjust the maximum current, which can then be adjusted from 0 to 100% using the control pin. We'll leverage this ability to change the maximum current if there's more white or infrared light required, since this value can be tweaked to push the LEDs to their maximum of 1000 milliamps. Now, let's talk about how this controller is able to regulate current by opening a model that I've created to demonstrate this point in LTSpice. To demonstrate how the switch mode power supply controller is regulating the current through these LEDs, I've constructed a simple model of a switch mode power supply controller and arranged the components in a similar way to how the IC I selected functions. On the left side of the screen, you can see the schematic, which I created based on the manufacturer's reference design. On the right-hand side of the screen, you can see the LTSpice schematic, which demonstrates how simple current regulation can be achieved using 2 op-amps and a ramp generator. While this is being used as a current regulator, it is actually regulating the voltage across the RSense resistor with respect to this voltage reference. It just so happens that the current flowing through this resistor is also flowing through the load, due to the way that the circuit is designed. Notice that I've labeled the nets of this LTSpice design to coordinate with the labeling of the pins on the current regulator IC and the nets on my schematic. Specifically, the VIN, set, LED pause, neg, switch nodes are similar to the way that this is laid out here. Notice the switch, VIN, set, etc. Now, in order to vary this load and create some interesting plots for you, I am using this voltage source as a way to simulate the addition or removal of LEDs. In this case, it's a parameter that's stepped from 1 to 6 LEDs and then multiplied by the forward voltage of a red LED. This regulator model consists of 3 main components: an error amplifier, here labeled current sense, which will be used to create a voltage that will be able to adjust the PWM duty cycle, the triangular ramp generator, which sets the frequency that this converter is operating, and the PWM generator that combines the two to drive the low side switch and create the current regulation. Even though this is a very simple model of the way that this regulator IC is working, the output ripple will be larger than a more sophisticated model, but it can regulate the current fairly well considering its simplicity. We'll measure the ripple performance of our current regulator implementation in a future video, and compare that back to what we see here. Now, in order to create the graphs that I've prepared for you, we need to run the simulation. Now this simulation takes a long time to run. Because it takes a long time to run, we'll jump ahead to when this simulation is complete. We can talk about the results. Now that the simulation is running, let's talk a little bit about what's going on here. Here, this is a voltage reference. In this case, it's set to 0.1 volts, but in reality, this would be much easier to achieve with a diode to create a 0.7 volt voltage reference, and then a resistor to ground to allow some current to flow through the diode to achieve the 0.7 volt forward voltage drop. In this case, since we're living in LT Spice, I'm going to use an ideal 0.1 volt source since that is the reference voltage of this chip. This, while it may look like an op-amp, is actually a comparator, which is a lot like an op-amp but optimized for railing one way or the other when the condition where it would go high or low is met. In this case, when the positive input is higher than the negative input, it will turn the output on. And when that condition is not true, it will turn the output off. By adding this resistor and capacitor, I'm going to filter out the pulses, the positive and negative pulses, and turn that into a steady state DC voltage, which will be compared against this ramp generator signal. So think of this as a voltage that is floating higher or lower to compensate for the load power required. The actual value of that signal is not as important as its relative position on the ramp signal. That relative position on the ramp signal is what will achieve current regulation. Another way to think of this is that when there is not enough voltage drop across this LED or not enough current, this output will flip high. When this is high, it will charge the capacitor through this RC network, raising the feedback voltage. As the feedback voltage increases, that will increase the position on the ramp signal and cause the PWM generator to leave the MOSFET on for longer than it would have otherwise. In a similar way, if there's too much current flowing through this resistor, there'll be too much of a voltage drop, so it'll flip this signal low, which will turn down the feedback voltage a little bit, which will reduce the amount of current going through the low side switch. In this way, there's a feedback network achieved, and when there's too little current, it will increase it, like we see here, and when there's too much, it will decrease it, like we see in this overshoot. With a more complex control system, the overshoot can be eliminated almost entirely. However, since we're looking at the steady state values, we aren't too concerned with the transient part of this simulation. Let's zoom in on the part that we are interested in. Now that we've zoomed in, we can clearly see that the shape of this waveform is changing. The reason why the shape of this waveform is a little different is because the more LEDs that we have in the load, the more slowly that current will build in this inductor. You can see that as more LEDs are added, the slope is decreased. That's because of the fundamental equation of an inductor. However, it's important to note that the difference between the steady state current values is actually quite small, considering that we're varying the output power by a factor of 2,600%. By a rough calculation with cursors, I determined that the steady state value was varying by approximately 30 milliamps. That's the RMS value, not the peak-to-peak value, or about 9%. Considering how much the output power difference is varying, that's pretty small. It's worse than I would expect from the switch mode power supply controller we're using because it was custom built for current regulation, but it's pretty good for a couple comparators and a simple feedback configuration. Notice that it's near-centered all of these waveforms around our 333 milliamp set point. If you would like to learn more about any part of this simple switch mode power supply model, let me know down below and we can dive into this a little deeper. But for now, let's conclude this video. I had a lot of fun today, creating this switch mode power supply controller model in LT-Spice, and I really enjoyed sharing it with you. I hope that it helped you to understand how the switch mode power supply controller IC is able to regulate current through our LEDs. Next time, we're going to talk about what I did to sync the heat away from the 30 high power LEDs in the half-inch grid, and how I was able to lay out this design on a 2-layer board. Most of all, I hope that you learned something great today, and I hope to see you again soon.